It only looks at the subscript 1. Subscript 1, so there's going to be two types of features. There's word association, input-output association features, that's 1, and transition features, that's 2, which I'll talk about in the next slide. One of the beautiful things about this notation is that now, suppose we didn't want to just use an indicator feature, right? We had some arbitrary features of our words, right? Like phi of, we could just say phi of x, right? So now we can say, like, for example, let's see, like if we had just other features, like what's an example? Like we could have an entire feature vector on the words. For example, a feature vector could be something like fish is also fish is closely related. Fish is cold-blooded, right? Like if there's a feature that says cold-blooded, right? So if fish were a noun, it would be a cold-blooded animal, right? That could be a feature, and we can activate that within this representation. So here, this phi of x is just an indicator vector, but more generally, it could be an arbitrary feature representation. So now the question is, why is there a subscript 1 here? The reason why there's a subscript 1 here is because there's two types of features that we use for the CRF, for the basic conditional random field notation. The other type is transition features, right? So now, phi of AB is if we transition from B to A. So the first feature in this feature vector is 1 if and only if B equals start and A equals noun. The second feature is 1 if and only if B equals noun and A equals noun. The third feature is 1 if and only if B equals verb and A equals noun. The fourth feature is 1 if and only if B equals start and A equals verb. And so it's an exhaustive Cartesian product of all the possibilities. Again, if you think about that transition matrix of parameters A, if we flatten it, you can think of this as indexing into a flattened version of that parameter matrix. For example, phi sub 2, the transition features of noun comma start is 1 in the first feature dimension, 0 everywhere else. The transition feature on verb comma start is 1 in the fourth feature, 0 everywhere else. And so on and so forth. Yeah?
Is there a reason there's not a superscript in this feature?
Just for simplicity, you can have a superscript and you can condition on the fact. So if you have a superscript, the only thing that buys you is you can condition on the word as well. Right? So in general, you could say, well, you could say something like, I really care about noun to verb transitions if the current word is fish, right? And you can absolutely have that. It's not required for the homework, and I just put in the simplest version of this. But more generally, yes, you absolutely can put in more features. And if you want to do that, then you have to add in superscripts that can index into the input sentence. But because in HMMs, the tag transitions actually ignore the input sequence of words, we're just going to do a direct analogy from that to the CRF formulation, but more generally, you're right.
Do people, and it might just be another way of writing a model, if people think about like time-varying Markov processes, think that there's like a time dependency probability, then wouldn't that be another way of indexing with J's on this?
Yeah, you can go crazy. You can like index anything you want. Like this is just the simplest version of a CRF. Yeah, just like in normal logistic regression, you can add whatever features you want. And some of you might be doing this for the Kaggle competition. In the CRFs, you can have whatever features you want. Yeah. As long as they structurally obey verb tag transitions, and as long as they structurally obey the basic assumptions and the basic restrictions of these two feature vector formulations. This one can only depend on a pair of tags and possibly the word. This one can only depend on a single tag and a word, right? You could have arbitrary features as long as it obeys those restrictions. Okay. Yeah.
So if you made a time tag, you could have that in the image.
Yeah. And obey those restrictions is what allows Viterbi to be efficient. Right? But otherwise, you can use arbitrary features. Okay, so this is the old scoring function, right? We score a sequence, an input sequence, output sequence pair as the sum over the jth input output token and its relationship to the jth input token. That's a score. That's a number in this parameter matrix. And the transition from the previous token to the current token, that's a score. We sum up all the scores, and then we get the score. Then this goes into the exponent of the numerator, and that's how we model conditional functions. Here's the new scoring function. It just looks like this. No A's, no O's, just W. So A, you can think of W as a flat, as A flattened, let me think about it, as O flattened concatenated on A flattened. That's W.
What happened to the subscript on phi?
Oh, because phi is now A.
Oh, the entire, okay.
So phi is now this.
Okay.
Yeah. So, yeah. The reason why this is nice is because if you're implementing this, right, you write a subroutine that says compute phi, right? It gives you this long vector, but now you can just treat it as a linear model. You can just like if you implement logistic regression gradient descent, like, well, you just instead of having an x that's given to you, you have a subroutine that computes a feature vector given the x and some y's. And now you just, and then now this is your feature, right? And then you just run logistic regression gradient descent. Yeah?
Just make sure I have this right. So conditional alignment field in the original feature space is exactly identical to logistic regression in the new feature space after we transform it.
You can, let's see. Both conditional random fields and logistic regressions are conditional probability models that are log linear, which means that it's a linear scoring function inside an exponent, right? And so the question then is, okay, is there an abstract formulation of that? The abstract formulation of that for a linear scoring function is a linear model over some features. And so for logistic regression, this phi thing is just x, right? It's just your original features. For conditional random fields, you create this new feature representation. And we've painfully through the last few slides showed that this new feature representation is basically equivalent to indexing into a flattened version of these parameters, right? And so you can think of W as a concatenation of a flat version of O and a flat version of A. And so what that means abstractly is that now that we've shown the equivalence, both conditional random fields and standard logistic regression can be written in this form for some definition of phi. The definition of phi for logistic regression is trivial, it's the identity. The definition of phi for conditional random field is this. Does that make sense, or? Yeah.
The purpose of doing this is to reduce the parameters we need to advance.
Actually, the number of parameters is exactly the same. There's two reasons why we do this. One, we already know how to do gradient descent for logistic regression, right? And by establishing this relationship, we can use that same code to do logistic regression for conditional random fields. At least the outer region. Okay. It's a way of making your implementation and when you just logically think about the problem more modular. Right? I have a log linear model. That's at the high level. It's a log linear model, which means I have some scoring function, and it's log linear in that scoring function. And the scoring function, I have a linear scoring function. It's log linear in that scoring function. A linear scoring function can always be written as your entire parameter vector transposed with some feature vector. It's just how you construct that feature vector that defines the linear scoring function. Any linear scoring function can be written in this form for some definition of phi. Right? Because a linear scoring function, by definition, is a linear summation of your components of your model parameter times some coefficient. Right? Yeah.
Does phi1 change with j?
It does, because phi1, the j indexes over which word in the token, in the input sequence you're looking at. So for example, for j equals 1, I only look at the first word. For j equals 2, I only look at the second word.
But you don't know a priori.
Well, you're given x as input. X is always, this is a conditional model, right? You're always given x as input.
Okay.
Yeah, so this thing only works if you fix an x. You give it a fixed x.
Oh.
Yeah, okay. So here, it's, yeah, you're given a fixed x and you're trying out different y's, basically. You're trying out, you're given a fixed x and a fixed parameterization of the model. You see this, you try out the score for different y's. Yeah?
In logistic regression, for different y's, the weights W are different, but here, in fact, for different y's, the weights are the same. Is it right?
So for binary logistic regression, there's only one way. For multi-class logistic regression, you can write W as W1, WL, okay? And then I could write my phi of y comma x equal to indicator vector of y equal 1 of x, indicator vector of y equals L times x, right? And now W transpose phi of yx is equal to WY transpose x. Right? So same abstract notation, just a different version of phi.
So it kind of seems like you're doing a lot of redundant calculation here, because like everything with phi2 has no j in it, but it's inside the sum, so it seems to be doing it over and over and over again.
Yeah, this is not necessarily the most efficient version of implementation, but if you want to write code that is somehow modular, there's going to be necessary inefficiency built in because you're not over optimizing to the idiosyncrasies of your specific phi.
Yeah.
So the point is taken, but it's a trade-off between how general you want your code to be, how easy it is to debug and implement, versus micro efficiencies you can do from optimizing this specific structure. There's always that trade-off.
Yeah.
So W is a stack vector. Marker sucks. Let me just put them right. So not everyone saw that, so let me just put them right on this row. Okay. So just an example. This is our scoring rule. So the W is our feature representation. It's summed in here. So this is the old notation based on an observation matrix. Right? This is the score associated with noun and verb. No, sorry, noun and fish. The score associated with verb and fish. The score associated with noun and sleep. The score associated with verb and sleep. Right? And so this matrix, if we flatten it, it looks like this. Right? And then if it so happens that we see noun and fish in the same token, like the first token is noun and the first output token is fish, then this first one will activate. We would add a score of 2 to our linear scoring rule in the old notation. You would do a dot product of 2 times only this feature being active. So again, you get a score of 2. Similarly for transition scores, it's on pairs of tags, pairs of adjacent tags, noun star, noun verb, so on and so forth. This is the old notation. We could take this parameter matrix, flatten into a parameter vector. Exactly one of these features will be active for any pair of tags, and it indexes into this parameter vector in the same way that it would activate an entry of this parameter matrix. Why the new notation? I guess we already talked about this. Just to summarize, if you once you have the right feature vector representation, it's much easier to think about in terms of like the outer loop for doing gradient descent. If you're doing gradient descent for conditional random fields, if you have the right implementation for the phi vectors and a couple other things, then the outer loop is just compute the gradient of w and update w with a step size, right? Just the same as logistic regression. And the other main reason why we do this, that we won't go into depth in this course, is that you can use almost arbitrary features in this featured route vector instead of just indicator vectors. Other features, like some global feature of the sentence, right? Like for example, I got a feature that says, does the word not appear in the sentence at all? And that could just be a feature vector. Right, so that's conditional random fields using the generalization of the logistic regression notation. The squaring rule, f of y comma x, looks like this. It's a linear squaring rule. I flatten all my parameter vectors into a single vector called w. I index into this using feature vectors that index into this word vector, sum everything up, exponentiate it, divide by the sum of all possible y primes, and that's my conditional random field model. This derivation I go through extensively in the course notes. The course notes on conditional random fields from last year are posted on Piazza, the link to it. I'm making some minor updates to it to clean up some of the typos, which will be probably released over the weekend. But if you want to get started, the link to the previous course notes from last year is already linked to off Piazza. Only cosmetic changes between last year and this year. So, just to hammer home the point, these are our models. Again, this is the same as the matrix coefficients, matrix version from the previous example, the same example, just in the vector flattened versions. Then we just do the same thing, right? We just sum over these 4 features, which activate these components of the model, which equal this. The exact same computation. These are the components of the model that get activated by this feature vector, and the rest are zeroed out. Exact same computation. Everything's exactly the same, just a different notation. Summarize a generic logistical model notation. All you need to do is define the right feature functions, and you're good to go. Okay, I'm just going to zoom through this because this is pretty self-explanatory at this point. Like Perturbi's done the exact same way. Maximizing finding the y with maximum probability given an input x is equivalent to just finding the y with the maximum linear scoring rule given an x. And recall the scoring rule looks like this. And so you maintain the length k prefix solutions, right? And then you recursively solve the next one. So if you have the length k prefix solutions for length k plus 1, you try adding some token. So this could be noun, verb, determiner, whatever. And then you compute the additional score. So how much does the score increase if I add this token? And again, the score increases, and this increase is just literally this term. You just add the score, add the model score for this feature induced by this feature vector, and that's it. Right, so if you have the right, if you have a feature vector, if you have a feature vector function implemented correctly, Viterbi is actually really easy, right? You just do this. Example. So for computing this, computing the Viterbi intermediate solution for this guy, the best length 2 prefix that ends in verb, you look at best all possible length 1 prefixes, take their score, layer score, you add this guy, and you take the best one. And let's say that was from noun to verb. You do the rest for the other ones. You repeat. Yeah.
So just a reminder why we use Viterbi, is it because we can assume like that?
It's because the feature vectors only depend on most pairs of tokens.
So we're assuming that
The Viterbi algorithm only, so first order Viterbi, this is first order because we only have pairs. First order Viterbi is not tied to the fact that you have a probabilistic model. It's a dynamic programming concept. It's tied to the fact that whatever scoring function you use, be it probabilistic or not, only has pairwise dependencies. Right? So therefore, if I just, since an argmax depends on just the scoring function, and the scoring function decomposes into pairwise sums, I need to return. And if we just think about it at a high level, this is easier to implement if you can implement this feature function correctly. Right? This is much easier to implement. Fewer things to keep track of. It abstracts away all the complexity of two different versions, 2 different parameters, A and O, indexing, overwriting lots of code. You just write a simple feature function subroutine, and then you're done. Right, so this is just going through the what I talked about yesterday using this notation. So this G, recall this G matrix is the e to this term, and now we just replace this term with our model vector dot product with the feature vector. Right? And we rewrite the probability like this, and the partition function like this. And the only thing that's changed from this slide from today, from Tuesday, is the definition of G, which is still the same definition, just use a different notation. Right? You get the exact same behavior. So recall the thing about the previous notation was that there were 2 things, A and O, you have to index into them properly. Here is just define your feature vector function, and then you're done. This is all stuff from before. Everything stays the same, basically. Do they have numerical stability, instability? So this is something that you have to deal with. This product can get quite out of control if m is the length of the sequence is long. And the way you do that is an observation. The way you do that is the observation that let's see. That you basically divide by it. So what you do is that at every intermediate step in the product, in the matrix product, you just divide by some constant. It doesn't really matter what that constant is. But you divide by a constant so that this doesn't get out of control. Right? And then by definition, the original G matrix is this new G matrix, the modified G matrix times all the constants. One constant that everyone likes to use is one that causes this thing to sum to 1. You don't have to use it, it doesn't matter. But now we can write the log of the partition function as, it's equal to this, but now you can write it's equal to this times the log of this. So you don't even need to keep track of these constants. Correctly, you just keep track of the log. And now this is no longer numerically identical because we renormalize every iteration so that things don't overflow or underflow, and then we just keep track of what we did, and then we just put it back on at the end, adjust for it at the end. So this is in the course notes for more details. It's very similar to what you have to do for forward backwards for the HLM, or forwards, I guess. Just. Training, so conditional random fields, like logistic regression, is trained using typically stochastic gradient descent. Just in the homework, you're using the same run.txt file as training data as the HMM homework. So there's only one training example, because there's only one input-output sequence. So in that case, stochastic gradient descent and gradient descent are exactly the same. So don't worry about which one you're using, it doesn't matter, they're equivalent. So you choose the W to minimize the negative log loss defined over sequences x comma y in your training set, which you take the form of the probability, and it looks like this. And the gradients are derived fully in the course note, they look like this. So the gradient with respect to the linear square function is very easy because it's linear. It's just the features that get activated, right? The gradient with respect to the log partition function is a little bit more complicated, but the upshot is that it's basically equal to the conditional probability of observing this transition in the data. And the optimality condition of conditional random fields, I believe I have it correct this in here as close to the beginning of lecture. The optimality condition basically says that at optimality, we set the gradient to 0. If you set the gradient to 0, and so this equals, or the negative of this equals this, because the gradient is the sum of these two, then you get something that looks like this. And all it says is that all it implies is that the empirical frequency counts in your training set of these features, I did it correctly here, is equal to the conditional expectation of these features according to our model given. So this is a necessary implication of finding the optimal solution, assuming we're not doing regularization. So what does this mean? Well, a conditional random field can be broken up multiplicatively, almost, into these components, right? Because it only directly models pairwise components. And so all it's saying is that given this structure of the model, I want these pairwise components, I want their probability of their predicted probability according to the model to match the empirical probability of the training set. That's all it's saying. So in this sense, it fully generalizes the optimality condition of logistic regression. Computing forward, let's see. So computing this, so gradient descent requires you to compute this term, right? So here's how gradient descent works. You're given some initial W, it could be 0. You compute the gradient with respect to the linear term, which is really simple because it's just the features that get activated. And you compute the gradient with respect to this term. So this term actually depends on W, right? This term depends on W. So then you compute this term, and then you take a gradient step, and you compute this again, you take a gradient step, you compute this again, take the gradient step. So at every time you do gradient descent, every iteration of gradient descent, you have to recompute this term. And so that's what the forward backward algorithm does. I won't just go through this really quickly because you've seen most of this already, but it's just in the new notation. Right. So half of this is computed using the forward algorithm. For every pair of AB, pair within of adjacent tokens in the sum, you compute the first half of this probability using forward, the second half using backwards. And this is something you should have seen before. This alpha vector starts as g of a comma start, and then you do this update. And the main difference between forward and Viterbi is that forward you sum over all the previous sequences. Whereas Viterbi you only keep track of the single decimal. So Viterbi is a maximizer, forward is a summation. And this is the formula you use to compute these terms given your curve model. And then you use this term to compute your gradient, do a gradient update, use that new model to compute this term again, because these terms depend on your model parameters, and then you just repeat until you converge. So this kind of right there. Numerical instability issues here happen as well with the alpha beta vectors. We've dealt with this for the forward algorithm for the HMM homework. And by the way, if you implemented the forward algorithm for the HMM homework using these G matrix notation, you just got to replace the definition of G and you're done. So if you have the code directly translates. So the observation is that you don't actually need to compute the alpha vectors to completion and then normalize. The normalization constant depends on the alphas as well, and therefore you could keep normalizing in the intermediate steps, and this appears in both the denominator, numerator, and the denominator, so it doesn't matter. Right? Okay, so just to recap, conditional random fields, they're first order sequence models. They use, in the simple version that we talked about in class, they use pairwise feature maps, so pairs of input tokens and pairs of output tokens in the input frame and the input sequence. You can define arbitrary features that obey this, that make use of only this information. You train by minimizing the negative log likelihood, which is just log loss over sequences, and use dynamic programming to help you with training and predicting. Any questions before I do a very brief overview of general structure prediction? Okay, general structure prediction. So basically from this formulation, we can talk about much more elaborate scoring functions than just pairwise scores over pairwise tokens, which is what first order conditional random fields give you. Right? So this is just the standard generalization is a second order conditional random field. A second order conditional random field basically takes, as a feature vector, depends on triplets of tokens instead of pairs of tokens. Right? So now we can model second order dependencies. Right? Given these two words, what should be the next one? We could use a much simpler version of the feature vector, right, and just do multi-class classification, multi-class logistic regression, right? So long as this summation has an efficient structure. So here, here for y, if y is a sequence, you only look at triplets, pairs of triplets of sequences at a time, finding the best